Context to an LLM is roughly analogous to short-term memory in a human being. It's a fixed size, sliding window of information that the LLM can hold in its mind at any given time. Now, when we're setting up a local LLM, we need to choose the size of that window very carefully. If we go too large, we exceed the VRAM that we have available, and we can cause performance to degrade, possibly significantly, possibly to the point where it won't run at all. If we go too small, the LLM won't have enough information in its mind to be able to complete the tasks that we put before it. But even if we choose the size of that window carefully, we still run the risk of exhausting it in a very long conversation or in a very long agentic tool chain. For example, the LLM has to invoke a tool, evaluate the results, invoke the next tool based on those results, and evaluate those results, and so on and so on. If it fills that context window, the window has to slide, and older information gets pushed out to make room for newer information, and the LLM forgets stuff that happened earlier. This can cause bad things to happen. For example, the LLM might contradict itself or go down a bad path where it tries to do the same thing over and over again and failing, or it might just start hallucinating. Okay, great. So you might think, well, let's just pick the largest possible window that our VRAM allows. Sure, great, but the problem is that the VRAM required to hold this context scales quadratically. If we double the size of the context window, we quadruple the VRAM that we need to hold it. So there's an art and a science to picking the right number based on our hardware, based on what model we're trying to run, and based on what we're trying to get it to do for us. So let's talk about how to configure context when setting up a local LLM to squeeze the most value out of it in a local environment.
No place like localhost. No place like localhost.
Okay, I'm logged into Jupyter. Let's take a look at this and see how it works. Now, when we fire up Llama Server, the parameter that we use to control the size of the context window is -c, and we give it a number. So here I'm saying 64,000, but 64,000 what? What is that? Is that bytes? Is that characters? Is that words? Is that kilobytes? It's none of those. It's actually tokens. But what is a token? LLMs reduce all of their input into numbers, a series of numbers called vectors, and it ends up with a gigantic grid of numbers that it can make sense out of. I'm not going to pretend that I understand how that works. I don't. But the long and short of it is that human language text tokenizes actually fairly well. Each word in an English language sentence might map to a single token, or if it's a long word, it might map to 2 or 3 tokens. I'm told that German language text tokenizes a little less efficiently than English language text because the Germans love their long compound words. But the long and short of it is that all input is reduced to these tokens. Even computer code. Depending on the computer language, it might be more or less efficient. Java, for example, has a lot of cruft like open and closing parentheses or braces or semicolons. All of these have to be reduced to tokens. So we are telling Llama Server to set aside 64,000 tokens for our context window. Okay, where does that get us? Let's fire that up. Let's keep an eye on NVTop as that loads. We'll see an initial jump in VRAM usage as the model file is copied into VRAM. This model is 16 gigs, I think. So we'll see an initial jump. There it is. An initial jump followed by a second jump. A little bit later, a few seconds later, we see that second jump in VRAM usage. What is that? That's llama.cpp allocating the KV cache. The size of the KV cache is driven by that context window size that I gave Llama Server on startup. 64,000 tokens equates to this much VRAM usage, apparently. So if I kill that and double it to 128K and start it back up, we'll see VRAM usage jumps again as the model is copied into memory, and then we'll see a larger jump to this new high. Now, in the intro, I said that context size scales quadratically. I did read that somewhere, but I'm not seeing that in my testing. I think it's more linear than quadratic. It might depend on the model. It might depend on the model. It might depend on the configuration settings we're using. I actually don't really know, but we can see that a 128K context window did have a bigger bump. It's a bigger second bump there than the 64K context window. So that second allocation is driven by the size of the context window. Okay, let me take that down one more time. There's a magical parameter you can give to Llama Server, which is 0. If I ask for a context size of 0, it's telling Llama Server just use whatever maximum token, or whatever maximum context window size that model supports. Now this model is Gemma 4 26B. This is my go-to model for testing purposes. It supports a context window size of up to 262,000 tokens, which is a lot. And we see this second bump takes it almost right up to the very top of the chart. And if you were paying attention down here in HTOP, you might have noticed that the system memory usage just jumped. that's bad. What that means is llama.cpp recognized that the context window I requested of 262,000 tokens is too big to fit into my VRAM. I've only got 24 gigs of VRAM, 16 of which is taken up by the model itself. So that leaves me with 8 gigs, which is not enough to store that much context. So I bring up the web UI now and ask it a question, my go-to testing question: what does the transient keyword do in Java? I'll bring up the magnifier so we can see we're getting mid-80s, about 86 tokens per second of generation. But if we look at HTOP, we see that all 6 cores are pegged. We don't want to see this. The GPU is pegged, that's great, but the CPU is involved. Why? Because the context window is partially in main system memory, and llama.cpp has got to get the CPU to coordinate with the GPU, and this is where performance falls off a cliff. We don't want to do this. So let's kill that. And let's go back to 64,000 token context window size, and I'm going to bring up the web UI. So our final token speed there was 82.6 tokens per second. If I start a new conversation and ask the same question, we see it jumps up to low 90s, 91-ish tokens per second. So it's and if we look at HTOP, we see that we don't have 6 cores pegged. We have got 1 core pegged. 1 core always seems to be pegged. I'm not sure why. I think it's orchestrating what the GPU is doing. But most of the heavy lifting now is being done by the GPU. This is optimal use of our hardware. And we did get a token speed boost there of a few tokens per second, which is good. Okay, great. So we can fine tune this. We can play trial and error until we find a value that's optimal for this hardware and for this model. Let's say, I don't know, 96,000 tokens. Great, I'm going to start up this model with 96,000 tokens in my context window. Great, but where does that get us? What can we do with 96,000 tokens? I'm sitting at 19.6 gigs of memory usage. I've got a few gigs not being used. That's not optimal. I could increase it a little bit beyond that. But let's play with this. Let's see what we can actually do with this. I'm going to drag 10 chapters of an unfinished novel. This is English language text. I'm going to drag it into context. This is 270 kilobytes of text. And I'm going to say, summarize these chapters. I don't care what the summary is. I just want to see, as it processes this, as we get to 10, 13, 17%, we're using 12,000 tokens and counting. I want to see, as we go through this, as it reads these chapters, this 270 kilobytes of text, how many tokens does that actually consume in context? We're halfway through, and it's only at 36,000. 2/3 of the way through now, it's only at 40,000. So I'm going to say about 60,000 tokens for 270 kilobytes of text. That's pretty good. Let's see what we end up with. 83, 87, 90% of the way through, and 97. So yeah, 61,000 and change. 61,000 tokens to represent 270 kilobytes of text. That's pretty impressive. I think with the full size context window, you could easily hold the entire novel, you know, like how all 20, however many chapters there are. That's pretty good. But what about computer code? How well would we do with that kind of experiment? I'm going to stop this because I don't actually need to see the summary here. How well would we do with computer code? Let's try it. I'm going to take 16 Java source files totaling 150 kilobytes, drop it into context and say, what does this code do? Again, I don't care about the answer. I just want to see, as it reads the code, I want to know how many tokens does it consume to process that much source code. So here we go. We're 10%, third of the way through. We're looking at 16,000. Halfway through, we're at 18,000. So it's going to be about 36,000 tokens for 150 kilobytes of source files. That's not bad. We're at 100%. Yeah, 36,000. 36,000 tokens for 150 kilobytes of source code in Java. That's pretty good. So even with a context window that is well below what that model supports, we can keep a fair amount of source code in context. Now, 16 Java files is not a lot. If we've got a non-trivial code base, even a modest-sized project is going to be bigger than that. So when we do agentic code work with this thing, we're going to want more context than that. We're going to want to squeeze more than 96,000 tokens out of this thing. But this is not bad for a first kick at the cat. We can tweak it a little bit more. And in fact, let's just try something. I'm going to kill it, and I'm going to say, you know what? Let's do it. Let's split the KV cache across the GPU and the CPU. I'm going to request the full 262,000. Did I time that? Did I time how long that took? Does it tell you how long it took? 28 seconds. It took 28 seconds. Let me magnify that. It took 28 seconds to do that at 62 tokens per second. Let's clear. And let's try that again. Exact same source files into context. What does this code do? Let's fire it off. Now it's going to be slower. We're not going to get the same. We're getting about 2,500, 2,200 prompt prefill. 2,200 tokens per second of prompt prefill. We're about halfway through. Yeah, so it's the same amount of tokens. It was 28 seconds last time. We're looking at... Took 20 seconds to read it, and then the generation time was 28 seconds last time. If we look at HTOP real quick, yeah, oh, the CPU is pegged. So it is slower. We're getting 61 tokens per second. It's not as much slower as I might have expected. Maybe we could live with that performance degradation, because this is actually not bad. If you compare the before and after, I think this is acceptable. It's a little bit slower, but not that much slower. 31, 32, 35 compared to 28. It took an extra 7 seconds to do that. But in exchange for that extra 7 seconds of performance degradation, we got a much larger context window. We now have a context window that is 262,000 tokens, which is enough to hold an incredible amount of stuff. So that's pretty good. I think scaling that up based on what we've seen, we could fit quite a bit of source code into context with this context window, and the performance is acceptable. We're getting 60 tokens per second of generation, even though the CPU has to get involved. So we can play with it, we can fine tune it, we can either pick the number that is just big enough to fit into our VRAM without spilling over into system memory and live with that, or we can say, you know what, I don't care if it spills over into VRAM, I'm going to work that little Core i5 right to its limits, and we're just going to live with the performance degradation. We can play with it and see how it goes. So in the next episode, we're going to finally hook this thing up to OpenCode and start putting it through its paces with actual agentic coding tasks. And we're going to play with the size of that context window to find that optimum spot, that trade-off point between memory usage and performance. And we're going to see what we can do with this thing when we actually start throwing coding tasks of it of varying complexities and seeing what it can do. Stay tuned for that. So in the next episode, we're going to finally hook this up to OpenCode and start doing... Oops, I touched the mic. Don't touch the mic. So in the next episode, we're going to shit. We're going to shit. If we go too large...